Hello, chemistry students. Here we are again in lesson 2, toxic tides, and today's lesson is on solubility. Now, this has a couple aspects to it, so it might be a little bit of longer videos. It has not only understand what solubility is and how it works, but also some quantitative portions to figure out how much salt or solvent is needed to dissolve a certain amount of solute. So, our objectives for today: compare what factors affect solubility of solids and gases, but also to be able to calculate, this is where the math comes in, the amount of solute and the amount of solvent that's needed at different temperatures to make a saturated solution. So what is solubility? Solubility is the maximum amount of the solute that can be dissolved into the solvent. So what's the solute? The solute is the thing that's being dissolved. And what is the solvent? That's the thing that's doing the dissolving. So in the case of, say, Kool-Aid, you have the water is the solvent, and the flavor or the sugar or the colors, they're all the solutes. They're the things that are being dissolved into the water. There's a lot of factors that can affect how fast something dissolves. First things first, some things just naturally dissolve better than others. Just the sheer nature between the compounds. And if we talked about in the last lesson about polarity of water, you can only imagine that if a molecule is polar, it's going to dissolve faster and better in water than if it was not. There's a cardinal rule in chemistry. One of them we've had earlier was hot glass looks like cold glass. This is probably the second most common cardinal rule of chemistry: like dissolves like. That means polar solvents dissolve polar solutes. Second, you can increase the temperature. If you want to increase the temperature, you can increase the amount of solute that is going to be dissolved. But also, you can increase the speed at which it gets dissolved into the solvent. You can stir it, obviously. That's kind of a straightforward thing. Stir it, you're going to make it where it gets to be dissolved in a little faster. It won't necessarily dissolve more, but you can get it to go in faster. Crushing it. Make it in smaller pieces. If you crush up the pieces of material, say you have a beaker with fine salt versus with, say, kosher salt, you stir those both, the fine salt is going to dissolve faster than the one that has coarse salt. And the last thing you can do, which only works for gases, is you can add pressure. So if you increase the pressure on the system and say you pump, say, carbon dioxide into it and put pressure on top of it, you can get more of the carbon dioxide to dissolve in, as well as get more the carbon dioxide to dissolve in quicker. So what happens during dissolving? Well, a couple things have to happen. One, if something's going to dissolve, say salt is going to dissolve in water, we'll use that as an example. First things first, that you need to have the molecules of water separate enough so that you can actually dissolve or put the salt molecules in between the water molecules. Now, the water molecules will dissolve each substance differently, but forces of strength, how attracted they are to one another, is going to play a big role. So here's a video showing how water would dissolve salt. So what we have here is sodium chloride, and the greens are yellow. Greens are the chlorines and the silvers are the sodium. You'll notice the water molecules, the negative side of the water molecules, grab the positive pieces. And the positive sides of the water molecules grab the negative pieces. And it tears apart the salt crystal, dissolving it and pulling all the pieces of sodium chloride into the water solution. Again, notice that you have the chlorine is attracted to the positive sides of water molecules, and the sodium is attracted to the negative side of the water molecules. So there's three different degrees of saturation. There's unsaturated, which means I have less solute in the solvent than would be the maximum amount. There's, for every single combination of solute and solvent, there is a maximum amount. That is saturation. If it's unsaturated, it means you've added less So you're going to have a sufficient amount of the salt dissolve completely, and there'll be no more salt floating, no more salt crystals in the material. However, if you have a saturated solution, you're going to have the solvent holding as much as it can, and there should be some undissolved solid remaining in the flask. Why is that? Dissolving is a constant process where the salt is being dissolved into the water, and the water is letting go of the salt particles to go back onto the crystal. And it goes back and forth and back and forth. As long as there's salt or the solute in the solution down here, as long as there's solute already there, that exchange of some come off, some come on, some come off, some come on is going to be capable. So it's going to be a saturated point. Now there is one other sneaky little one, and that's called the supersaturated. Now what's this supersaturated solution? That's when we can manage to get more than is the maximum amount of solute to dissolve. Now how do we do that? Well, one thing you do is you take a solution, and we already said, we'll see a little bit in a graphical form, that as you increase the temperature, you get more of the solute to dissolve. So what we're going to do is we're going to take the solvent and warm it up, and try to warm it up enough to allow more that would be dissolved at room temperature to fall, to absorb, to dissolve into the water. And then we cool it down. Slowly we cool it down until just a little bit more solute is dissolved into the solvent. Now, this here is a picture of sodium acetate, or maybe it's ammonium acetate. They both do the same thing, where they got it into supersaturated solution. They dropped a seed crystal in there, and it started making all these crystals form. Here's a video that shows the same thing. So what they're going to do, what's in this big flask is a saturated. You're going to take a really, really tiny particle. Now you can see when it comes in with the spatula in a second, there's like a speck on the end of it, a very tiny speck of salt. See the little white spot? And he's going to drop it in. And as soon as he drops it in there, you see these spikes start forming. Those spikes are the sodium acetate that was in solution that should not have been in there because it was super saturated. And now, as soon as you agitate it, it allows those crystals to form and come out of solution. This is a very endothermic reaction. It gets really, really cold. Not to the point of freezing, but notice how little water is in there. That's almost entirely the sodium acetate crystals. You can get a whole lot of sodium acetate into water in this method. So let's talk about solubility and the quantitative side of it. Okay. Many, many solids and gases will dissolve in water. They will dissolve at different amounts. You can, like, for instance, you can get carbon dioxide dissolve into water to make soda. You get the flavors dissolve in the water. If you increase the temperature, you can dissolve more solid. But think about it. Does that work the same thing with gases? Well, not necessarily. If you've ever had a soda, a carbonated beverage, and you left it out at room temperature, what happens to that saturated beverage? It usually gets flat. Why is that? The gas molecules escape the solvent, the water, as it gets warmer. That's the opposite of what happens with solids. So with gases, as you increase the temperature, you increase the gas molecules' kinetic energy, making them more likely to escape from the solution. To get the gas to dissolve, we already mentioned before, one way to do it is to increase its pressure, but the other way to do it is to decrease the temperature, make it really cold. So we're ready to embark onto the math part. The part where we're talking about these things that are called solubility curves. Now, don't get overwhelmed just yet. There's a lot here to cover, and we're going to do our best job to try to walk through A lot of different things you could do with these solubility charts. So let's look at this. This is an example of a solubility curve. Notice what we have here. The line represents saturated solution. And for each compound, you see there's different compounds associated with each line. Now, how do we read this? Well, if I were to take, say, this compound here, potassium nitrate, and I were to say at 60 degrees, I could dissolve 105 grams of potassium nitrate into 100 grams of water. That's at 60 degrees. But if I were to do the same thing at, say, 40 degrees, go up there, look like now I'm like 64, just shy of 64 grams of potassium nitrate can dissolve into 100 grams of water. So it depends on the temperature. So the question here is, which one of these compounds, which one of these pieces on here are going to be gases? Well, if you guessed HCl, NH3, and SO2, you'd be right. Those three are gases. How do I know they're gases? Because they decrease in solubility as the temperature increases. So let's talk about what you can do with these solubility curves. So in your notes, you should have something that looks like this for every one of these example problems. And we're going to walk through trying to analyze and solve for whatever they're asking for. So first problem I gave you said, how much potassium chloride will dissolve in 100 grams of water at 50 degrees Celsius? So what you're going to do is take 50 degrees Celsius at the bottom and run a line up to the potassium chloride line. And then to find out how many grams will dissolve 100 grams of water, you go over to the left-hand side, you run a line, and you see where it intersects, and that intersects really close to like 42. So the answer to this question is simply, I can dissolve 42 grams of potassium chloride into 100 grams of water to make a saturated solution at 50 degrees Celsius. That's just reading the chart. Take your temperature, run it up to whatever the compound is, run a line over to the left, the y-axis, see where it intersects. Where it intersects is the amount of solute that can dissolve into 100 grams of water. So what you have here is going to be a conversion factor. 42 grams of potassium chloride can dissolve in 100 grams of water. We have a conversion factor. Okay, let's use it. Let's try this question. How much water is required to dissolve 100 grams of sodium nitrate at 20 degrees Celsius? So the first thing we always will have to do is find out how much sodium nitrate will dissolve in 100 grams of water at 20 degrees Celsius. Okay, so we go to a 20 degree mark, run up the sodium nitrate. We run our line over to the y-axis and see how much will dissolve into 100 grams of water. And I see that I have, we call it 89 grams of sodium nitrate will dissolve in 100 grams of water. Now, we want to dissolve 100 grams of sodium nitrate. So we're going to need more water than 100 mils or 100 grams. Let's do a little conversion factors and dimensional analysis to figure out how much. So we'll start with the 100 grams of the sodium nitrate. And then we're going to take this conversion factor here we just made, and we're going to decide to use it such that our grams of sodium nitrate is going to cancel. When these cancel out, I'm left with grams of water, which is what they're asking for. So 100 grams times 100 grams of water divided by 89 grams, and I see that it's going to take 112 grams of water to dissolve 100 grams of sodium nitrate. You're using what you get off the chart as a conversion factor. Try another one. How much potassium nitrate will dissolve in 1.5 kilograms of water at 40 degrees Celsius? Well, the first thing we always do is find out how much of the potassium nitrate will dissolve in 40 degrees Celsius, 100 grams of water. So we find it on the table. We take 40 degrees, we run it up. We go over to the left and see where it intersects. And I'm going to say that's 63. So I'm going to say that I have 63 grams of potassium nitrate can dissolve in 100 grams of water. But I don't have 100 grams of water. I have 1.5 kilograms. So I have 1.5 kilograms. And back to middle school, you know there's 1,000 grams in a kilogram. Kilograms cancel. That means I have 1,500 grams of my water. So that would be my starting point. I'm going to start with 1,500 grams of water. So let me get rid of those markings. I'm going to take my 1,500 grams of water. This time I'm going to put the conversion factor in this orientation. So again, I get to cancel out my grams of water. See, whatever I've given, I want to make sure I cancel out so it's going to be at the bottom of the fraction. And then I do the math. I take 1,500 times 63 divided by 100. I get that I can dissolve 945 grams of potassium nitrate into 1.5 kilograms of water, most specifically at 40 degrees Celsius. Let's keep going. So next one, how much potassium nitrate will dissolve in 750 grams of water at 60 degrees Celsius? So this is very similar to the last one. So I'm going to ask you to pause. Try this one on your own, and then when you're done, restart the video. So how'd you do? So the first thing we got to do is we got to find out what that intersection is. So we're going to take our 60 degrees, run it straight up to the line for potassium nitrate, run the line over, and that looks like it's really close to 95. I'm going to call it 95. I have 95 grams of lead nitrate will dissolve in 100 grams of water. But I don't have 100 grams of water. I have 750 grams of water. So I'm going to take my 750 grams of water. I'm going to use this conversion factor. Do I leave it the way it's written, or do I flip it upside down? So if you did this right, you left it the way it is, because I want to make sure my grams of water cancel. So I'm going to write it just the way it is. Oops. Every time I do these, my phone goes off. Okay. So I guess erase that weirdness there. Get my little dot back. Okay. So I'm going to take, and it's going to be 95 grams of lead nitrate, PbNO3, 2. And then I do my math. Let's see what that looks like. If I get rid of all markings. And I do this, get 750 grams of water, add 95 grams of potassium nitrate per, oh, it should say lead nitrate. That's my bad. Lead nitrate per 100 grams of water. Again, this should be lead nitrate. I made a mistake. A compound. And then I do the math, 750 times 95 divided by 100, and I get that I can dissolve in 712 grams of lead nitrate into 750 grams of water at 60 degrees Celsius. Let's keep doing. Let's keep trying. Next one, take the same 750 gram of solution, and I'm going to cool it down to, let's see, it's going to cool it down to 30 degrees Celsius. So what's going to happen? Well, what's going to happen, you should know, is that I'm going to have a different solubility. We had, at 60 degrees, we had 95 grams would dissolve in. But at 30 degrees, let's see, I'm like at, I don't know, it might be 66, 65. I have a different amount. I can't draw a straight line. I have a different amount. So some of it is going to fall out of solution. That's called a precipitate. When stuff falls out of solution, it's called a precipitate. So let's see. Go up, go over. Yeah, we'll call it 65 grams of lead nitrate per 100 grams of water. Awesome. Then I'm going to find out how much will dissolve in 750 grams of water. So I did the same thing. Still have the same error here. That's my oops. Sorry about that. That should be that compound. Okay. I take 750 grams of water times 65 grams of lead nitrate per 100 grams of water. I do that math and I find out I can put 488 grams of water, 488 grams of lead nitrate into the 750 grams of water. However, that means when I had, at the higher temperature, I had 712 grams of water, 712 grams of lead nitrate, and then I do it at a cooler temperature, if 488 grams of lead nitrate, that means I'm going to have 224 grams of my lead nitrate precipitate out into the bottom, going to fall out and become the solid at the bottom of the container. Okay, so there's a bunch of different ways to do the math part of these problems. It really comes down to taking the chart, turning it into a conversion factor, and then using that conversion factor to solve for whatever you're looking for. So, one thing to consider, talk about, is the concentration of dissolved oxygen in dissolved minerals in the water is very, very important for aquatic life. So, one of the things about the Chesapeake Bay that's interesting is it's an estuary, which means close to the ocean, it is very salty, has a very high salinity, and up towards the north, where the rivers are coming in, it's very, very freshwater. It changes. So it's partially salt water, partially fresh water. It's called brackish. It's somewhere between based on which force is more. If there's more rainwater, the bay is going to be more freshwater. If there's less rain, the bay is going to be it's going to be more salty. One of the unique things about our Chesapeake Bay is the fact that it requires it to have a salinity that's somewhere between ocean saltwater and freshwater for some of our most prominent life to survive there. Crabs, here's oysters, clams, all that stuff really, really needs to have brackish waters. Something that has a set amount. Now, again, you increase the amount of water, fresh water from the streams and rivers, you're going to decrease the concentration. And that's going to be bad for some fish. Almost always happens the other way around. In the summertime, when we get these droughts, there's not a lot of water. Our Chesapeake Bay gets very, very salty. And we see more and more ocean life coming up into the bay, deeper into the bay, and also then killing off a lot of the things that need to have a set salinity somewhere between freshwater and ocean water. So that's about it. That's lesson 4. Hopefully that was helpful. Please just practice those problems. If you have any questions in class, do not hesitate to ask your friends or me. I can always walk you through examples of the solubility calculations again and again until you get it. So until next time, toodles.